Hi guys, good morning. So today basically what I'm going to talk is all about EIS, electrochemical impedance spectroscopy. So basically when we focus on the DSSC, dye-sensitized solar cell, we are saying that electrochemical impedance spectroscopy is important because when you run this test you can get the resistance, which are series resistant and charge transfer resistant. So you can prove your data. You can see that if the resistance is big, that's why your current voltage analysis is lower, so you can get a lower efficiency. If the resistance is small, you can get high efficiency in dye-sensitized solar cell. So what happened when you study about the counter electrode? Typically people will get two semicircle. As you can see, this is one semicircle and this is two. You can see that semicircle is something like an arc. You can see that if you imagine a circle, we are saying that semicircle is half of the circle. From the graph, as you can see that they have two semicircles. All three of them have two semicircles. And we call that here, this is the semicircle at high frequency, and this one is the semicircle at low frequency. The same for the black one and also for the blue one. This is the semicircle at high frequency. This is the semicircle at low frequency. So what happened? So in EIS, the important things is to know, we want to know about the RS and the RCT. RCT is for charge transfer resistance and RS is for the series resistance. We want to have a smaller RCT for a good electrocatalytic activity towards redox electrolyte, while the RS, you can see the RS is the value that we can obtain at the first here, at the first starting up for the Nyquist plot. You can see that RS, the smaller RS is good, that indicate that our sample is have higher conductivity compared to the others. As you can see here, P dot multi-wall is more conductive compared to P dot NCC and P dot RGO because the RS of P dot multi-wall is smaller than that. Then when you compare with in terms of RCT, you must calculate using the software. In this the what we call it, the diameter is, you must calculate the value of the resistance in the unit of ohm. So before we are talking about that, we are saying that typically in DSSC, if you study about counter electrode, you can get two semicircle. Basically, one semicircle at high frequency, which is the first semicircle, indicates the impedance between counter electrode and electrolyte, whereas the semicircle at low frequency, the second semicircle at my right, indicates the nurse deficient impedance of iodide triiodide redox couple. So in counter electrode, you can see two semicircles. One is the impedance between counter electrode and electrolyte. The other is the semicircle between inside the electrolyte itself. You can see that. But if you study about the photoanode, typically people will get three semicircles because in this counter electrode, the procedure is different. We are using symmetrical dummy cell for two electrode system, which means that you only use your counter electrode as both two counter electrode, the same one, the identical counter electrode, and you sandwich together, and then you test with the software or potential stat, and then you can get, you run the FRA, which is the the software for the EIS, then you can get the result, the Nyquist plot. But it is different in the case of photoanode. When you are studying about photoanode, you can't use identical, what we call that, identical two electrode system dummy cell. You cannot use that. You must use a complete set consisting of photoanode and counter electrode sandwiched together. That's why in the photoanode you will get three semicircles. One semicircle at the beginning indicates the resistance between the photoanode and counter electrode, and electrolyte. The second one is the resistance between counter electrode electrolyte. The last one is the resistance of electrolyte itself. So typically, if people study normal about a photoanode, you can get three semicircle. First one, the resistance between the photoanode, counter electrode, and electrolyte, the resistance between three of them. And in the middle is the resistance between counter electrode and electrolyte. And the last one is the resistance between the electrolyte itself. So it's different because the method for you calculating it is different. So you can try yourself, but sometimes people, even we are saying that typically in counter electrode, if you are study about counter electrode, we got 2. If we study about photoanode, we got 3. But certain people only can get 1 or 2 because some material, if you are using a material that have higher resistance, it might overlap the rest of semicircle. It might, we are saying that it might produce only one semicircle. It depends on the technique. It depends on the solution that you use. So you can try yourself because it is important to what we call that, to run the EIS analysis, because from the Nyquist plot you also can plot the Bode plot. From the Bode plot you can calculate the electron lifetime. From that you can see that the smaller resistance is corresponding to a higher electron lifetime. When electron lifetime is higher, your power conversion efficiency also higher. That's why we are saying that EIS is one of the important factor. Either you study about photoanode or counter electrode, this test must be done if you want to prove your sample is good. Thank you.